Okay, let's proceed with another example, which is a very nice example. We are going to analyze a case that is called a leak before break design. And this is relevant to pressure vessels. So let us analyze a spherical pressure vessel. Okay, so that's our sphere, right? Has a certain radius. However, the sphere is not perfect. Let's say there is a crack on its surface. Now, what I will do is I will take that portion and I will somehow flip it over here and draw it once again. So I'm taking a portion from the sphere surface. Of course, it has a certain thickness as well. So when I draw that portion, has the thickness, has the surface area, and it has a crack on it. Now, number of remarks for eventual calculation purposes. This green block is certainly not flat. It has a curvature because it's taken as a piece from the sphere of the surface. Eventually, what I'm going to assume is that that crack is very small. When it's very small, with respect to the size of the crack, this thing will be larger, but still, with respect to the size of the sphere, this green block will be small. So this is an exaggeration. So it's as though, imagine the Earth looks, with respect to us, it looks flat, right? Because our dimensions are very small with respect to the size of the Earth. So if the size of the crack is sufficiently small, with respect to the crack, the surrounding material will look almost flat. So I'm going to idealize the surrounding material to be almost flat. And eventually that the width that I am considering here, I'm going to assume that's sufficiently large with respect to the size of the crack. We'll come back to that in a second. Now, therefore, what I seem to have locally, if I'm going to consider the scenario as eventually a fracture scenario, what I am going to consider is a plate with a crack in it. We'll discuss the geometry of the crack a little bit more soon, but what we have is tensile loading. There is an internal pressure, but the pressure, if it's thin-walled, it's something I can omit. I can omit the normal stress in the radial direction. I'm certainly going to do that here as well. Simplifies my life. But there are two tangential stresses that are equal, which are, let me just denote them with a single arrow. There is a tangential stress sigma t, which is equal to PR over 2t, and also another one in that direction. And they are equal because it has a spherical geometry. Now, eventually I'll do a fracture analysis here. And if I did not have these tangential stresses, the horizontal normal stresses, it looks like my ideal prototypical plate with a central crack, irrespective at this point of the geometry of that crack, which is also important. But if these are not there, then the situation is identical. But we do have a normal stress in the other direction as well. So now in general, the way you load your structure is important. So whether or not there are tangential stresses here are important. But it turns out that in this case, these tangential stresses are equal in both directions. So this normal stress is equal to that value. And for that reason, it turns out there is no effect of this component of the normal stress. Okay, this is what one can at least find from the literature. So the normal stresses in that direction for the purposes of fracture can be omitted. Okay, but for the purposes of fracture, okay, we're going to omit. If I want to look at yielding, they're certainly important. But to decide if fracture occurs or not, it turns out I can handle this case as a prototypical scenario. This is not something we can deduce on our own. A fracture mechanics expert has to tell us that this can be done. And that's the way I'm going to address that problem. Okay, now the second issue is that this crack has a certain geometry. So now what I will do is I will go ahead and look at the geometry of the crack within this plane. So what I'm seeing is a red line, but really, in reality, if cracks do form on pressure vessels, they might form from the inside or the outside, but strangely, they form in some sort of a penny-shaped region, as a penny-shaped or a coin-shaped form or portion of a coin. So if I zoom into now this portion, okay, so I'm going to draw this portion again over here. So looking from above, what I see, okay, these are the two surfaces. Okay, this is the inside of the vessel, this is the outside of the pressure vessel, and of course it extends further into both sides, and there is a so-called penny-shaped crack here. So now let's think about the following question, and let's think about also, let me mention why the situation is important. So first of all, whenever there is a crack, right, the crack can grow or may not grow, but eventually fracture is an issue if there's a crack. That's the first thing that comes to our minds whenever we see a crack. So I like to make sure that this pressure vessel is free from any possible fracture. The reason I want that is because when fracture occurs, it's catastrophic. This crack will very rapidly propagate, and in some strange fashion it will branch into different portions. It will split the surface, the sphere, into smaller portions, and those portions, under the action of the internal pressure, will rapidly move in different directions. Sorry about that. So this pressure vessel, if it fractures, it splits into pieces, and those pieces rapidly move away. So it acts essentially something like an explosive, something like a bomb. So you don't want that to happen. So if you have a gas canister at your home, or if you're carrying a pressurized gas from one location to another, or for that matter, any type of pressure vessel, you don't want any issue with fracture, because that is going to be very unsafe. Now, the problem is that even though there might be a crack, and that crack is smaller than the critical crack size that might cause fracture and hence explosion, the crack might grow with time. So even though at the beginning it's too small to cause fracture, it might grow with time and it might cause fracture. So initially it's like this. Suppose you examine the structure and you do see a crack, or you say that it's safe, but you check let's say several months later and you see that the crack has grown. This happens in particular if there is cyclic loading of that pressure vessel. So for instance, you remove the gas inside, you transport it, it gets unpressurized, and then you pressurize again to transport gas again, unpressurized, you remove the gas, and so on. You fill empty, and then each one is a cycle of loading. So at each stage, the crack will grow. Okay. Now, as the crack grows, what will happen is the size is increasing, the area of the crack, so the situation will become more and more critical for fracture. The value of K1, in this case, the stress intensity factor, will increase and approach towards fracture toughness. But something else can also happen. What can happen is that this crack can ultimately hit the inner surface of the vessel, and as soon as it hits it, well, a crack has two surfaces that are freely movable away from each other, so there is a tiny but certainly a certain amount of gap between them. So as soon as it hits the surface, what will happen is that the pressure pressurized gas inside will leak through the crack to the outside. And when that happens, the vessel is unpressurized, and although the crack is large, stress intensity factor will go to 0 because the gross stress will be 0 because the pressure is removed. Gross stress has to do with P. So when the gas leaks, the vessel will be unpressurized, it leaks, and you are not going to face fracture. Now, of course, leakage is another scenario. It's probably also not something that you desire, but leakage is something you can detect safely with sensors, whereas explosion, if it occurs, is catastrophic and sudden. So what you would like to have is a design such that if there is a crack and it will grow, the design will be such that at the point of possible leakage, fracture is not a concern. So in other words, this design should leak before break instead of break before leak. All right, so let's examine that idea a little bit more. So the idea that we are proposing is that this crack has a width of 2a and the plate has a thickness of t. And leakage occurs if the size of the crack reaches, the radius of the crack reaches the thickness of the plate. In that case, the gas will escape from the inside to the outside. Now, how can I check if leak before break is satisfied? The way I can check it is I can calculate the value of Ki for a given crack size of A equals T. Okay? So when A equals T, leakage is about to happen. I calculate the K1 value at A equals T, and I compare it against K1C. If it is less than K1C, then leak before break happens. Why? Because the crack grows. When A is equal to T, it will leak, but at that stage, or up to that stage, K1 is never equal to K1C. So you don't have fracture, and so you're safe. Another way to check this would be that you calculate the critical crack size for fracture for your loading scenario, that's that scenario, and you compare it against the value of the thickness. If the critical crack size is larger than the thickness, the crack needs to grow to a value of AC for fracture to happen, but before it reaches AC, it will hit the value of T and the pressure vessel will leak and you are safe from fracture, right? So otherwise, when A is equal to T, if this is greater than Kc, or if you calculate AC, it's less than T, you have break before leak, which is not something that we would like to have. Okay, so that's the idea of a leak before break design, and it's practically important. Now, there is one issue remaining before we can proceed with an analysis, and that issue has to do with the shape of the crack. Now, remember, what we would like to do always is calculate K1, and that is going to be the form factor, the gross stress root pi A, and compare it against K1C. However, the form factor functionally, its form depends on the geometry of the crack as well. So what we have assumed always was a through thickness crack, a crack that extends all the way through the thickness of the plate. In this case, it doesn't. It's a penny-shaped crack. But what we are going to do is we are going to assume at any stage, although this is our criterion, to apply at least in our analysis. So in general, you don't have to do this. In general, there is a form factor that applies to this scenario. But what I'm going to do is at any stage, I am going to calculate the value of F as if the crack was a through thickness crack. Now, this is not physical. It's just an idealization for the purpose of analysis. If it were physical, it would leak already. But what I'm going to do is I'm going to assume that the crack is not of this size, even when it's penny-shaped and like this, but actually of that size, okay? So I'm going to assume it's larger, and hence the value of K1 that I will calculate, because the crack size is now assumed to be larger, the value of K1 that I calculate with this scenario will be larger than the K1 value corresponding to the physical penny-shaped crack, and hence I'm predicting K1 to be larger than it is, and I'm comparing it against K1C. So I'm going to be conservative. So I'm going to be safer. Now, I might be too conservative. I don't want to be too conservative, but at least in the context of this example, that's the way we are going to approach. So we're going to approximate or assume for the purposes of this analysis as a through thickness crack. And that is a conservative assumption. Okay, so therefore, what I end up with is a through thickness crack, a width 2a, and the plate has a width of 2b. Now, what is b? We're going to come to that in a second. And it is loaded in tension. There is a normal load in the other direction, but for the purposes of fracture, we have said that we can omit this normal stress in the other tangential direction. Okay, so now because this is the prototypical ideal case that we have considered, we know how to deal with it. So now let's go ahead and actually solve an example that has to do with this setup. Okay, so the question that we have is a particular case when the pressure is, the internal pressure is 6 MPa. Okay. The radius is 750 millimeters. Inner radius, outer radius doesn't really matter because the thickness is just 10 millimeters and it is certainly thin-walled. I do need material parameters. The fracture toughness is 187 MPa square root meters, and the value of the yield strength, which I will eventually need, is 760 MPa in the context of this example. And I have three questions. One, do we have leak before break? Two, what is safety factor on fracture with respect to the value of the stress intensity factor? And three, what is the safety factor against yielding? All right. So let us go ahead and solve this problem. Now, the first part, do we have leak before break? So the first thing we need to do is we need to calculate the gross stress. So in this case, SG is equal to sigma T is equal to PR over 2T, which is equal to, if you plug in the numbers, you'll find it to be 225 MPa. All right. And what I want is I want to calculate K1, which is F SG root pi A. Okay. And I would like to compare it against the fracture toughness, which is equal to 187 MPa square root m. The value of A that ensures this equality is the critical stress. So my idea eventually, you see, I will calculate the critical stress, size of the crack, and I will compare it against T. If it's larger, I'm safe. Okay, so I'm trying to calculate the critical crack size. But you see, I do have a problem. I do know what SG is. It's 225 MPa. So this is known, but what is the value of F? Now, because I don't know AC, I don't know what F is. So I need to somehow make an assumption. So I'm going to assume that alpha is less than the 10% limit, which is 0.4 for this prototypical scenario. We've encountered that number at least once before already. Okay, so with that assumption, I can go ahead and plug in here K1 equals f of 0 sg root pi ac, and I can now, because f0 is equal to 1 for this scenario, then I can go ahead and immediately solve for AC. And I will find AC to be, from this equality, to be 220 millimeters. So one outstanding question now is that I have made an assumption, and so I need to check my assumption. And to check my assumption, I need to somehow compare AC against B. Well, the question is, what is B? Because it's the width of the plate, but I took that width to be arbitrary. I took a piece from the surface. And what I said is that if the crack is small enough, then the width is, if it's sufficiently large, even for a very large width, probably that plate is going to look smooth, flat with respect to the curvature of the sphere. So it really shouldn't matter too much. But now I need a value. I need a value to check if that is reasonable or not. So the width of the plate is a measure of the in-plane. It's a measure that has to do with the in-plane dimensions of the sphere, and the in-plane dimension, if you like, has to do with the circumference, and the circumference is a function of the radius. So I'm going to take B to be the radius. Now, this is a very shaky argument presently, but I've taken a number now. I'll take B to be the radius as a measure of some reasonable in-plane dimension. So in that case, if you do that, you will obtain alpha to be 0.293, 220 divided by 750, and which is less than 0.4, and therefore my assumption was fine. I'm okay. I am within the 10% limit on F, and therefore the value I have calculated is safe to within that assumption. Now, if you're not happy, what you can do is you can experiment with this expression, and as an example, use a much harsher value for F, because if F increases, the critical value of AC will decrease. If it decreases, perhaps it comes very close to T or even go below it. So I'm going to use a harsher value of F. Here we are using 1 because I'm using the 10% limit. Why don't we just go ahead and assume F is 1.6, okay? So that's a rather large value. In fact, let me correct this. I am sorry. I'm going to use alpha equals not less than 0.4, but I'm going to assume that it is 0.6. And when alpha is 0.6, F comes out to be 2. So it's going to be twice as high. When it's twice as high, then we can calculate AC to be 254 millimeters. Sorry, 54 millimeters, which is a much more severe value because it's smaller than 220. So now let's go back. What are we trying to do? I'm trying to calculate the critical crack size, and I'm idealizing this complicated loading scenario as such. There are various levels of approximation. I'm omitting that stress for the purposes of fracture analysis. I'm assuming this plate is flat, that the width can be quantified through the radius, and that I'm being actually here quite conservative. I'm approximating the penny-shaped crack with a through-thickness crack. And then I go ahead and calculate the critical crack size for that problem for this given loading, and I find it by setting it equal to K1C to be 220 millimeters, right? And when I do that, I am done, because I check and alpha is less than 0.4, so my calculation appears to be reasonable to within that 10% accuracy discussion. So now, am I safe against failure? I am, because 220 is much greater than the thickness, which is 10 millimeters. So I am safe against fracture. It leaks before breaks. So the crack will grow. For fracture to occur, it needs to go up to that value, but before that it will hit through the thickness and then it will leak and depressurize, right? Now, if you are not happy with this choice of R, you can choose a much harsher value of alpha. I chose it to be 0.6. In that case, you get AC equals 54. You still are significantly larger than the thickness. So probably what I'm doing is a reasonable assumption here for the purposes of back of the envelope calculation that we are doing over in this example. Okay, so that was part A. Now we're going to look at part B. What we would like to determine is the safety factor on the on fracture with respect to the stress intensity factor. Now, the safety factor is KIC divided by the value of the stress intensity factor that is relevant to my problem. Now, the upper part is easy. It is seems to be a material property, right? But the way we are going to formulate this problem, right? I have already calculated that the left-hand side will be equal to K1C. So instead of writing K1C here, I'm going to write that expression, which is correct. Okay? This is the value of F that corresponds to AC. And I will scale it by what I deem to be a critical case. Now, that critical case is F, or K1, evaluated at the most critical scenario towards fracture. Now, I know that the pressure vessel is going to leak before fracture. So as the crack size grows towards T when leakage will occur, the situation gets more and more and more severe. The severest value of K1 is when A takes the largest value possible. The largest value possible is the thickness value. So the largest value of K1 that I can possibly see in this scenario is the thickness value. Okay? So what I can therefore do is I can simplify SG is the same, root pi cancels, and I'm going to cancel F2. Now here is a caveat. I'm doing another level of simplification here, which you don't need to do if you plug K1C equals 187 directly and take the value of F corresponding to the value of T. But I can do that simplification over here. What I'm going to assume that this F is negligible. It's almost 1. Okay, and this F certainly is negligible because T is very small. Therefore, these F's are not there. And therefore, the ratio is simply AC over T. I know the value of AC to within my approximation. I know the value of T, that's the thickness. The value comes out to be 4.69. Okay, so that's the safety factor on the stress intensity factor against fracture. So it seems that we are quite safe against fracture, again, to within our crude approximations. Now let's go to the third part. So we are just wondering what kind of an issue this pressure vessel has. We know that it will leak before break, but it might also yield, and I may not want yielding to occur either. So the question is, the crack will start growing, and at some point it might leak. It certainly will not fracture, but at the point of leakage, there is a certain safety factor on fracture, but perhaps it will yield before it even leaks, right? And I may not want that to happen either. Let's get back to what I was saying. I may not want yielding to occur either. So I'd like to check my safety factor against yield as well. So the way we do that is we calculate the safety factor on yield as the yield strength divided by the equivalent normal stress. So remember, the criterion that we use to check for failure, either for brittle or ductile materials. So when I talk about failure, I'm referring to what we discussed earlier, that is the limit of the region on elastic behavior. So we're checking the limit to elastic loading, and if we try to force the material behind that limit, something will happen. If it's brittle, it will break apart. If it is ductile, it might yield. If it's significantly ductile, it yields a lot. If it's not so ductile, then it will not yield so much. But in any case, there is a limit on the critical value of the equivalent normal stress that we can go up to. Because it's ductile, because we're limited with the yield, we're provided with a yield strength, we know that it's ductile, so I'm taking the critical stress to be sigma naught, and I'll scale it with some equivalent normal stress. So we will in general, remember, have a complicated three-axial, three-dimensional state of stress. We convert it to the principal picture. The directions of those principal stresses don't matter. We are assuming isotropy always on the background, apart from our discussion of anisotropic elasticity. So those are fed into a function that delivers us the equivalent normal stress. And that equivalent normal stress can be calculated either using the maximum shear stress, or so-called Tresca criterion, or using the octahedral shear stress, or so-called von Mises criterion, right? So I have a ductile material. I don't really know at this stage which one I should use. But I do know that the principal stresses are equivalent to the stresses that I already have, which are sigma 1 and equals sigma 1 equals sigma 2 equals PR over 2T. And I will assume, as I have done presently as well, that sigma 3, which is the normal stress in the radial direction, it's omittable because it's proportional to simply P. It's minus 6 MPa in absolute value, 6 MPa only. So compared to a value of 225, it's very small. So we have a state of really plane stress. And we know that for a state of plane stress with equal principal stresses in the remaining two directions, it really doesn't matter whether I use the von Mises or the Tresca criterion. Both of them will predict exactly the same equivalent stress. Okay, and that comes from, at this point, you may wish to either use the equations for von Mises or Tresca criterion, or you may wish to remember the failure surface for the Tresca and von Mises criteria in the sigma 1, sigma 2 space when sigma 3 is 0. This is Tresca, and a smoother line in the first quadrant would be von Mises. We are presently at that point, sigma 1 is equal to sigma 2 equals PR over 2T. And then you can go ahead and calculate what the equivalent stress is, and that is equal to essentially 225 MPa as well, because the von Mises criterion looks at the largest difference between, the Tresca criterion looks at the largest difference to calculate sigma bar between 1 and 2, between 2 and 3, and between 1 and 3. Therefore, the largest difference is the difference between 1 and 3 or 2 and 3, which are the same and which are equal to PR over 2T and which is equal to 225. So this quantity is 225 MPa. That quantity is 760 MPa. So our safety factor on yielding is 3.33. So in other words, when we have this loading, so I have that loading and the safety factor on yielding is already 3.33. It's independent of the size of the crack. So here I'm calculating sigma bar without any consideration for the presence of the crack. So then the crack will grow, and at some point leakage will occur, and the safety factor, the worst kind of scenario I can have, is a safety factor with 4.64, which is larger than that value. So it seems that I have a design at this stage where we have leak before break, and moreover, for this given pressure value, yielding is more of a concern than fracture.